All right, so now we're looking at chapter 3, stoichiometry. It's one of my favorite things. I don't know why I have that first slide on there. Stoichiometry. So look at some concepts. There's not a ton of topics on here. Most of the stuff we're going to be doing is in class, working on stuff together. So we're going to kind of brush over a lot of the actual sample problems, but we'll do them together, just so we know. And this is by definition what a mole is. 1 mole is equal to 6.02 times 10 to the 23rd, whether it's going to be atoms, molecules, formula units, marshmallows. 1 mole means that number. It's like a dozen. It helps us. What it does is in a normal laboratory, we wouldn't be able to work with 1 atom of substance. But by using the mole concept, we can go ahead and work comfortably in the lab by using a balance that deals with grams. 1 atom, 2 atoms, 15 atoms, they're impossible to measure for us at this point in time. It usually gets the capital symbol N to represent Avogadro's number, but N in chemistry tends to get used a lot. Here are some examples of 1 mole of each of these substances. I believe, so just so we're looking at it, the water is 18 milliliters. There's the sand, or the salt, which is 58.5 grams, the aluminum, which is 27 grams, and the sugar in the background, which is like way bigger than all those. And I'm not sure it's on the actual left-hand side of that substance is. Molar mass is very similar to what we call molecular mass, which we covered in the last chapter. You do it the exact same way, but in this example, what we're doing is we shift a number that's small. Like if I said I had 1 molecule of water, then I can say that it's 18 atomic mass units. Well, an atomic mass unit is 1.66 times 10 to the negative 24th gram. It's a very small number, very difficult to work with. So you can imagine if we go in our laboratory, we look and our scale has 3 decimal places. Well, 1.66 times 10 to the negative 24 should have 23 decimal places. So it's not a number we can actually measure. So we have to take it from something small and switch it over. And Avogadro's number allows us to do that. Okay? And when we do it, we take a look at this one, and we want to calculate the molecular elements, right? So if this is a molar mass, we can do the exact same thing with the atomic mass. The only difference is we said 1 molecule of water equals 18 nanometers. For our example now, it would be 1 mole of water equals 18 grams. And gram per mole is written like that. It's the same as saying, so for the oxygen, instead of saying 13 grams per mole, we could say 1 mole of oxygen equals 32 grams. All kinds of information in chemical formulas. It all basically relates to the mass. Nothing really else. How it's lined up is not kind of ignored. Ways to convert stuff over. I'm not going to spend a lot of time on this because I'm going to show you a different way. I'm a big believer in just paying attention to how things cancel. So for me, things have to cancel out. If they don't cancel out, we did it wrong. And all you have to do is figure out how they cancel. More of the same. Get it in mole. You can go from atoms and molecules into the amount, or moles. You can go from mass into the amount. You usually don't go directly from mass into atoms or molecules. So the mole is the middle quantity. We're going to do all this together. Fun, fun, fun. Right? All right, the amount-mass relation for compounds. We're back at the same place. We do it the exact same way. Again, mole is in the center. Right? We determine the actual mass of the actual compound using molar mass. Mass percent works on the same concept. But the question would ask something along the lines of, what mass percent is hydrogen in water? So what you have to do is, you're worried about hydrogen. So you'd figure out the mass of of hydrogen in water. So you take 1 gram per mole, or as the top one says, it's an element, 1 AMU for every element of it, and you double it for water because there's 2 hydrogens, and you divide by the total, which is always how you do percent. You always divide by the total of the compound. Mass fraction is the same. Okay, it's just done the exact same way, but we don't multiply by the 100%. We usually leave it as a decimal. Okay, this part should be new to all of you. And so there's a little bit that goes with this. The AP likes to take it, see it's elemental analysis on the definition. The AP likes to do something called combustion analysis, which we'll do a day on. One of our labs will be based on this stuff. Essentially what the empirical formula is the simplest or lowest whole number ratio that we can determine the substance. We can do it experimentally pretty easily. So for example, if it's hydrogen peroxide, the lowest whole number ratio is 1H and 1O. The molecular formula shows the actual number. Okay, so for hydrogen peroxide, the molecular form is H2O2. Right, that's how it works. They're related. If you double the empirical formula, you would get hydrogen peroxide. And we'll spend a lot of time on this part. And the molecular formula gives the actual number of each. So you know exactly how many atoms of each substance are present. And you do this by taking the empirical formula, okay, and the molar mass, we'll call it the molecular formula for now mass, molecular formula mass. Dividing the molecular formula mass by the empirical formula mass gives you a whole number multiple. We'll call it lowercase n. So this shows the relation between the molecular formula mass and the empirical formula mass. And we call it a lowercase n most of the time. It's a multiplier. I'll show you in a little bit. Skip this, come back to it. The way to do it, right? Organic analysis, they can go ahead and scrub it. We're not overly worried about this. We'll do it a different way. And we'll do lots of problems with this. And let's just show you the relation between totally different substances. They have the same what we call empirical formula. The empirical formula is the lowest whole number ratio. So it's CH2O for this one. And when we take a look at it, we can see that there's lots of possibilities. The whole number multiple is the n. You calculate it by taking the empirical or the molecular formula mass and divided by the empirical formula. So if you took this one, gathered up all the masses, calculate all the masses, and divided by this one by its mass, it gives you 2. So you would take this empirical formula and multiply it all by 2 to get the acetic acid. Lots of good things, and it shows you, the bottom ones show you how they look. Things behave totally different. All right, a chemical equation. We use the chemical equation to represent what we call a chemical reaction. The thing about it, though, is we can write a chemical equation with anything we want to write for. We can write it for a physical change we want to. It's just something that goes ahead and shows you how the things come together. And we can even make sure it obeys the law of conservation of matter on the paper. But it doesn't, the reaction doesn't have to work. We can write an equation for it, but it doesn't have to work. Okay? And so we have an example of it here. We're burning magnesium. Magnesium is that gray, bluish kind of atoms on the bottom. When you burn something, you're always reacting with oxygen. That's how it works. Things don't burn without oxygen. And we produce MgO2. Right? And we can see that it will gain mass. If I took the magnesium solid and I weighed it out, and then took it again at the end after it was burned, it should actually go up in mass. And does that mean it obeys the law of conservation of matter? It went up in mass. Well, it would, because we took a certain amount of O2 out of the air. And in order to go ahead and really do the calculation, we'd have to actually adjust how much O2 we actually submit to react. Okay? The arrow means yield. The reactants are on the left-hand side and the products are on the right. That's the way it always works. We want to balance it. We want to make sure the numbers work. And in order to balance things, we change something up front. Only the number up front. So for example, if I wrote MgO, it's because Mg is a +2 and O is a -2. So that works. The charges cancel. So I can't change either one of those numbers because ionic compounds are always empirical, the lowest whole number ratio. Always. Probably not quite right, but close enough. Okay? So I would have the right numbers out front, in front of the Mg, in front of the O2, in front of the MgO. We call those coefficients. The bottom one says states matter in there. I get kind of lazy myself and I tend to leave those off, but that's okay. Balancing, we'll do that. Here's a way to visualize it. We have octane, we react 2 molecules of octane have to react with 25 molecules of O2 to produce 16 molecules of CO2 and 18 molecules of H2O. In these scenarios, both sides have the same number of atoms. For example, there should be 16 carbon atoms on the reactant side and 16 carbon atoms on the product side. And there should be 36 hydrogens on the reactant side and 36 hydrogens on the product side. So this should be consistent. Again, we'll do this as well. We can kind of judge this one for a little bit. We definitely have a chemical reaction. Things have been broken apart. We'll look at this together. All right, so that mentions the word coefficients. It's the number we write out front. After we write the chemical equations correct, we can only balance the equation by writing numbers on front, and those are called coefficients. And they represent the number of moles of each substance. We can use the balanced chemical equation to determine what we call a mole ratio, which is important. It's on the bottom. Use it as a conversion factor. And they're related to moles we saw before are related to mass. So that's significant. We need to use them to move forward. Okay, we see a chemical reaction that's obviously according to the bottom, balancing. So obeying the law of conservation of matter, 204.09 equals 204.09. All right, now we get a little trickier with this kind of thing, right? We want to go ahead, we can do amount, mass, number relationships, which you've kind of already seen, right? But we have in the middle there a mole ratio. This is molar ratio balanced equation. So we can go from the mass on this side of substance A into its amount, and then use a mole ratio to go ahead and switch it from substance A into substance B and then pop it back into the mass. And we will do together, we'll do together, together. I'm going to eliminate this one. We don't need to know that right now, but real quick, just can eliminate. Just so we know, chemical reactions tend to occur in sequences. They're not all direct way that they work, right? So we always use an example, magnesium plus oxygen yields magnesium oxide. Yes, that probably would be a direct one because it happens so fast. But other reactions make things we call intermediates. And sometimes these intermediates get used up and aren't even included in the overall reaction. We're going to highlight this second semester when we do kinetics. We're going to talk about something in particular called a reaction mechanism. Writing out the equations. Right. Now, limiting reactants and percent yields are the last couple things I think on in this chapter. You've done these before, but to the extent you need to, probably not. The limiting reactant is important because it determines how much product you make. When I have a chemical reaction, I have something called a limiting reactant and something called excess. I don't really worry about the excess because it's excess. I have more than I need. There's more of it, so it's called excess. I'm worried about the limiting reactant. The limiting reactant gets used up during the course of the reaction, and it determines how much product I can form. So all that matters is the limiting reactant. Here's an example. The top one is a kind of a chemical equation you can use to go ahead and make one sundae. 2 scoops of ice cream, 1 cherry, 50 milliliters of syrup, and 1 sundae. I happen to have the actual materials in B. How many sundaes can I make? Well, I can make 2. Well, why can I make 2? Well, I don't have enough chocolate syrup to make any more, or fudge, whatever you want to call it, to make any more than 2. Once I use 100 milliliters of the chocolate syrup, I don't have any anymore. I'm out of luck. Whereas I have plenty of cherries and plenty of vanilla ice cream. 2 scoops. Gotta have 2 scoops. And we'll look together. Look together. We will look together. Excellent. Together. We'll spend a lot of time on this thing. Reaction yields. The theoretical yield is what you calculate. So you would take one of the reactants, the limiting reactant if you had a choice, limiting reactant, and you would go ahead and convert it into the product. That yield means product. So the theoretical yield would be if I did it perfectly. If I ran the reaction and took the limiting reactant, used all of it up, had plenty of excess other reactants, used up the actual limiting reactant, then it should produce the theoretical yield. We've assumed at this point in time that all the products we've made are theoretical. They're perfect. There's nothing else going on there. There's no side reactions. There's no problem with the reaction going to completion because it just doesn't. We're just going to assume they work perfectly. The actual yield is what actually you get. So you run the reaction, you produce a certain amount of product. This is what you actually made. You were in the lab, you did it. Okay? So when we want to figure out the theoretical yield, when we want to figure out the percent yield, what we would do is take the actual yield, if we given in the problem, take the theoretical yield, we'll have a way to calculate it from the limiting reactant, put it in this equation, it's almost always going to be less than 100%, unless we're dealing with gases. There's a little side thing, right? What happens if we get a side reaction? We don't get as much product as we're supposed to get. So in this example here, the 51.4 kilograms of silicon carbide, okay, is recovered, which means it is the actual yield. And the 100 kilograms of sand, which is a reactant, okay, is what we use to figure out the theoretical. And again, we'll do this together so you can see it. And that's going to be it for chapter 3.